So when beginners learn machine learning, one of the first common problems that they come across is to do basic classification. And often beginners are very confused about the fact that we can use the sigmoid in the binary classification and the softmax in multi-classification. And many beginners wonder what is the relationship between this sigmoid function and the softmax function. And how can you derive the sigmoid function from the softmax function? In today's video, I'm going to show you exactly how to derive the sigmoid function and the softmax function, and how we can deduce the sigmoid function from the softmax function. So let's get started with the very basic question. And the question is, given an input z is element of the real numbers, how can we decide in a classification problem to which class z belongs to? So in binary classification, we would have class 1 and class 2, for example, and we want to say for a given input z, does it belong to class A or class B? And it's always a good idea to not start with the full problem, but to break it down and go from there step by step, iteratively. And so it's a good idea to think about probability and about chance, because in the end, we want to say that the input z belongs to a certain class with a certain probability. So let's break it down. So I got here a very basic example. So we have a dice which we can roll. It's just a very basic die. And what we want to do is we want to get the probability that we get a number which is larger than 4 when we roll the die. And well, we know the face of a die are 1, 2, 3, 4, 5, 6. And we want to have a number larger than 4, so 5 and 6. So we have 2 out of 6. So if we get a 5 or 6, these two outcomes are what we want to have. So the probability of getting a number larger than 4 when each face of a die is equal probable is 2 over 6. And we also know that q plus p is equal to 1, because q is nothing else than 1 minus p, because we know from probability that the probability that something happens plus the probability that it doesn't happen should sum up to 1. So 1 minus p is 6 over 6, because that's 1, minus 2 over 6 is equal to 4 over 6. So what is the chance that we get the outcome that we want? So a number larger than 4. And this is given by the odds. And how do we compute the odds? Well, we just take the probability that it happens divided by the probability that it doesn't happen. And this is 2 over 6 over 4 over 6. So the 6 cancel, and what we get is 2 over 4. And 2 over 4, that's just 1/2. So why is the chance or the odds equal to 1/2? Well, because there are 2 events, and that is rolling the die and getting a 5 or 6, and there are 4 events to roll the die and get a 1, 2, 3, or 4. And that is why the odds are 1/2. So the odds are equal to p divided by 1 minus p. So, and let us notice some properties of the odds. If p is equal to 0, the odds are also equal to 0. If p is equal to 1, the odds is equal to infinity, because we get 1 over 1 minus 1, and that's a 0, and 1 over 0 is infinity. So the odds, when we see it as a function, it's mapping the input, which is a probability, so going from 0 to 1, onto the space of 0 to infinity, which is not included. But what we want, we said we want a given input z, which is continuous, so it's element of the real numbers, and we want to map it onto a probability. So how can we do that? How can we use the odds in order to achieve our goal and to find the function which we need? Well, first we notice this interval goes from 0 to infinity. But what we want to have is that it goes from minus infinity to infinity. How can we achieve that? Well, we can use the logarithm in that case, because every number which is smaller than 1 will be mapped to a negative value by the logarithm. And this is called also the logit p. And this is defined as the logarithm of the odds, which is dependent on p. So the logarithm of p over 1 minus p. And this one, so the logit of p, is a mapping from 0 to 1 onto minus infinity to infinity. So basically, this is the real numbers, right? And now we notice we want to find a function which maps from the real numbers onto 0 to 1. So what we have to do is we have to invert the logit here. So let's find the inverted function. So we set it like z is equal to the logarithm of p over 1 minus p. And what we have to do, we have to take the exponential in order to get rid of the logarithm. And we can invert it, so it's easier to resolve the equation after p. So this is 1 over p minus 1. So we get 1 over e to the power of z plus 1 is 1 over p. Now we just gotta invert it again. So we got p is equal to 1 over 1 plus 1 over e to the power of z. And this can be written as 1 plus e to the power of minus z, right? And this is the sigmoid function, right? And the sigmoid function is a mapping from minus infinity to infinity onto the interval 0 to 1. And this is exactly what we want for binary classification, right? We want to give an input z, and we want to obtain a value between 0 and 1. Perfect. And so this is again the real numbers. This is exactly what we wanted. And now we can ask the question, is this sigmoid function really a probability? Can it be considered as a probability? And yes, we can, because p of z is equal or larger as 0. We can see that because when we plug in the limit z going to minus infinity, what do we get? Well, we get 0, right? Because we have 1 over 1 plus e to the power of minus z, and if z is going to minus infinity, it cancels with a minus in the exponent, so it's positive infinity, and e to the power of positive infinity is a very large number, so 1 over an infinite large number will converge to 0. And we can also say that pz is smaller than 1. You can see that by taking the limit, but this time to plus infinity, and what we get is 1, right? Because e to the power of minus infinity is a very small number, it converges to 0. So we have 1 over 1 basically, and 1 over 1 is 1. And what we also know is that, let's denote p of z, which is the sigmoid, let's denote it as the probability that we get the class k given an input z. And this should be equal to 1 minus the probability of not getting class k given the input z. And we know already this guy. This is what we showed with the sigmoid. And we wanna calculate this guy. So what is it? It's 1 minus the probability. So 1 minus the sigmoid function which we had. So 1 minus 1 over e to the power of minus c. And this is 1 plus e to the power of minus c, 1 plus e to the power of minus c. This is equal to 1, right? Minus 1, 1 plus e to the power of minus c. And now we can, this one cancels with that one. And so we have e to the power of minus z, 1 plus e to the power of minus z. And this is the probability of not being of class k given the input z. And we can check the probability of being of class k given input z plus the probability of not being class k given z is equal to, and this is 1 over 1 plus e to the power of minus z plus e to the power of minus z divided by 1 plus e to the power of minus z. And this is 1 plus e to the power of minus z over 1 plus e to the power of minus z. These cancel out, and this is equal to 1. So as we can see, the sum of the probability of obtaining the result plus of the probability of not obtaining the right result, which we wanted, is equal to 1. And the probability is indeed in the range of between 0 and 1. So far, so good. So how does the sigmoid look like? So if we have to plot it, we would have the z on the x-axis, and we would have the sigmoid on the y-axis, and we would have, and it would cross the y-axis at 1/2 and would converge for very large z's to 1, and for very small z's, so negative values of z, to 0. And how can we do binary classification now? Well, suppose the probability that z is class k is equal to 0.8, so 80%. We need to have some kind of criteria in order to say that z is k or not. And a common way to achieve that is to pick a threshold. So the threshold could be 0.5. And now we could say, okay, if the probability is larger than the threshold, then we decide that z is the class k. And if the probability is smaller or equal to 1/2, we would say it doesn't belong to class k. So that is as easy as it gets. So the sigmoid function is suited for single class problems or binary class problems, because we can either say that we have class A and B, or we could say we have class K or not class K. This is the same, it's just a different wording. So we have a binary class, so let's write it in brackets, and we have a single label, right? So single label means that we need that when we train a machine learning model, we would need to tell the machine learning model what would be the right answer. And since we map the input set to a single class, we also have a single label. And now the question is, can we extend our finding to multi-class classification? So what we had is that the probability that that given z it is belongs to class k is a map from the real numbers onto 0 to 1. What we want to have is another function which will map from the real numbers, but this time it's a multi-dimensional space with the dimension that is equal to c, and c is the number of classes, and onto 0 to 1, and again multi-dimensional space with dimension of c, where c is the number of classes, right? So let's try the first ansatz in order to find s. So the first ansatz could be to say, okay, let's have z1 and let's divide it by a normalization factor. So for example, z1 plus all the values up to zc and so on. But this has the problem that zi is an element of the real numbers. The zi's can be negative, and e is going from 1 to c. And since zi can be negative, we don't have a probability here, but we need a probability. So what we need to do, we need to make z positive. And how can we achieve that? And we can achieve that by using the exponential function, because the exponential function, as we know, is always positive. So we could write something like this: e to the power of z1, e to the power of z1 plus up to e to the power of zc. We do the same until e to the power of zc, and again the normalization factor. Okay, so far so good. So this guy here would be the same for all the elements. It's the denominator and it's the normalization factor, such that we get a probability. And this guy here, this is the softmax. And we can write this as z of c, which is equal to, and with an index I, which is equal to the exponential to the power of z t, so the transpose of c, times wi. And we will talk about wi in a second. And the normalization factor would be a sum from k equal to 1 to c e to the power of z transposed wk. And where c is again the number of classes. So this is the softmax. Where wi, what is it? Well, it's 1 if the essentially the row index, so we call it index, is equal to I and 0 otherwise. So for example, W1 could look like this: 1, 0, 0, and where we would have 3 classes. So there are some interesting special cases with softmax. If we only have one class, what would happen is that as set of 1, so we would only have one I, right? Because I is going from 1 to c, e to the power of z1 over e to the power of z1, and this is equal to 1. This is the only case where the softmax is equal to 1. And c equal to 2 is z1 would be e to the power of z1 over e to the power of z1 plus e to the power of z2, and z2, because now we have 2 classes, would be this guy. You should notice one thing. When we have 2 classes, this should be actually the sigmoid, right? Because in the sigmoid case, we also had 2 classes. So when we have the softmax and we set c equal to 2, we should get the sigmoid. But we have to notice one thing. Why doesn't this look like the sigmoid? The reason why that is because the sigmoid is, as we defined it, is basically a one-dimensional function, right? It has a one-dimensional input, so a scalar, and gets a scalar output. So in order to retrieve our sigmoid function from the softmax, we have to say that, for example, w, so we have to project the one-dimensional, so the dimension out of the 2-dimensional space, which we have in the softmax case for c equal to 2. And what we can do is we can set w equal to 0, 1 and 0. And we can say z is equal to x and 0. And now, if we plug that into our softmax formula, what do we get? So what we get is, for the first element, so for I equal to 1, we would get e to the power of x, e to the power of 0 plus e to the power of x, which is 1 over 1 plus e to the power of minus x. This is exactly what we had the sigmoid. So in this case, what is sz with index 2? Well, it's e to the power of 0, e to the power of 0 plus e to the power of x. And this is e to the power of minus x, 1 plus e to the power of minus x. And this is the probability of being class k given minus x. And if you compare these two equations which we got, so 1 over 1 plus e to the power of minus x, and e to the power of minus x divided by 1 plus e to the power of minus x, this is exactly what we've calculated here, right? So here, this guy, this is e to the power of minus z divided by 1 plus e to the power of minus z. This is what we got for the second index, and for the first index we got the sigmoid. So the softmax is really consistent with the sigmoid function. And we can really derive the sigmoid function from the softmax function. And the softmax function, where can it be used? Well, as we said, it's used in multi-class classification and where we got a single label. And now you could ask, okay, what would we use when we had a multi-class classification problem and had multiple labels? So, for example, for a given input z could not be only in one class, but could be in multiple classes. And we will discuss this in a separate video. But here I just want to highlight, how would you decide in a multi-class single label scenario, given an input z, to which class it belongs. And we would decide it in the following way. So how could the softmax output look like? For a given input z, let's say it looks like this, 0.2, 0.6, and 0.2. So this has to sum up to equal to 1. This is the case, right? 0.2 plus 0.6 plus 0.2 is equal to 1. And what we do is, this is class 1, this is class 2, and this is class 3. So every row in the vector would correspond to a class, as we said. And we would just pick the class with the highest probability associated. So class 2 has a probability of 0.6. This is 60% larger than the other one of 0.2. So we would say that z belongs to class 2. This is how we do the softmax. I hope you liked this video. I hope it was insightful. And if you have some other ideas for other videos, write it down below into the comments, subscribe and like. And I hope I see you soon. Until the next time.